on the spot. You know the result on the spot. Okay. Some of them may concern about vibration. We also monitor vibration, and in fact, you'll find that all the vibration is well within the. Of course, within 10 meters is big, but further than 10 meters is nothing. It's well within all the construction limit. In fact, I published together with Peter a paper on vibration in. We can skip this. This is the picture when you show you. This is expensive equipment here, but this is the mass, and the chamber is inside here, and the part is below there, and then you can just run the test. I'll show you this one later. Now, I'm doing breaches. In case you do breaches across river or across the sea, see, this is a part you want to test, right? I can put the whole Statnamic on top of it, because this only 1/20 is 5% of the test, so very small. And then run the test, and that's it. I don't need to do, if you are doing static test, you need to have additional auxiliary part to put the platform and then put a concrete block like this, and then you do the jack and test it here, and then test it here. So this is additional supporting part. Right, in marine, this is going to spend a lot of money. Can you see that? So this supplement is not needed here. Can you see? I can put the whole thing on the part to be tested. That's it. All right, and we have done quite a lot of these tests in Malaysia, both in Western Malaysia and Sabah, Sarawak. So Sarawak is just north of your capital city. Same big island. What's the name? What's the island name? Kalimantan. Big island there. So we've done a lot of tests in Sarawak there on this test across the breaches across the river. So that is something very useful. Okay. So now that was the first method which I introduced a concept. But the really method I will introduce is who is this? Henry, can recognize this man. He's none other than your good friend Peter. Okay, and his team is Statnamic, which we worked together in the last almost 20 years now. Okay, so Peter, after Marcel, I hope what I say is correct. After he's about to retire from TNO, he said, "Hey, I'm going to invent a new method for my own company." So he developed a Statrapid method. Statnamic belonged to TNO, and then they sell to somebody else. That's a separate issue. But now Peter developed a Statrapid method. So Statrapid method, he don't play with fuel anymore, but instead he play with a special cushion. So you're going to drop a mass, which you can call hammer, but I don't like to call hammer. I like to call it drop mass. It's special drop mass. Put on something special cushion. I draw here, but actually it's a very special cushion. When you drop on that, this cushion was and deceleration of 20 times of G. A equal to minus deceleration of 20 times of G. So therefore, it produces the same force. Minus means the direction. So now the force is directly applied onto the power. So the magnitude is 20 mass times 20 times of G. That is a force. It's the same as Statnamic now, but except that now force is downward because of producing that deceleration and causing the power to push the power down. Now that's it. So that's called Statrapid. And of course, tell you newly created English word is static plus rapid load. Therefore, it will give you a load, and you can see from these pictures, the yellow color is a mass. You can call it or drop mass or whatever you call it. And then cushion here is a special cushion. I'll show you secretly a little bit. This thing will do this a drop height. So this thing will drop onto that and produce a force. Right? This cushion is different. It's not the PDA cushion. PDA cushion is to protect the power top only. It cannot perform the function of decelerating or whatever. Whether this cushion, the special cushion, will produce the A equal to minus 20 G. That is the secret. This cushion have to produce that deceleration. Okay, now these are secret pictures. I'm showing you the cushion. It can compress like this, and then you will bounce back. Okay, and then, okay, do I quickly show? So in short, I will put the cushion here, and then drop mesh hit onto it, and that will give you the force. Okay, now let me show you the real run, interesting run. Okay, let me show you. Yep, I hope you can see because this is important. Okay, I stop here first. Let me bring this away. How do I bring this away? I cross something. Okay. You can still hear me, Okay, you can see this yellow color thing is the mesh. All right, there's a gap here. There's a height, Of course, this height not much, but there's a height. Cushion is at the bottom. You can see and the power is below. Okay. Now in a few seconds, I'm going to turn on the video. You can see that this yellow color will drop, hit the cushion, and then bounce up. Okay, so watch carefully, Okay, coming up. You see that? Yellow cushion was here and drop and come back. See that? That's done. Over. And there's no big leak voice. So it's very smooth, very gentleman, very gentle. Very nice, right?
Oh,
everybody see that?
Hmm?
Everybody see? Right. Yeah, okay, I'll show you one more time. Okay, but this time very fast, at the very beginning, okay? I show you one more time. This one is a different one, but it's the same, See? And let me repeat this one. This one at the beginning. Okay, the one is here. There's a gap here, gap at the middle. The blue color you don't see. The power. This one you can see the power at the bottom. You can see there's a reflective white strip here. Later I'll talk about that. That is the one to measure settlement very fast using laser beam. It's a standard load cell will measure the actual force. Okay, so you can see very fast. This yellow thing going to drop, hit onto the cushion. Produce a deceleration, the force will load onto the power and then bounce up. When it bounce up, this machine can also catch on it. Once you catch on it, you can move to a different height and repeat the test. All right, so this machine can catch it and then move to a different height, drop again, and bounce again, catch it, drop. Okay, you see, very fast. See? Okay, it drop and then it bounce a little bit and then it catch. Okay? See the power is here?
Like hammer.
Look like hammer, but the trick here is not so much on the hammer, it's a cushion and also able to catch it. But it's more than a hammer. A hammer, if you don't have the right cushion, don't have the proper design, it can't work. So you need this frame to support it as well. Now, this frame, I should explain a little bit of this frame. This frame is very well designed because this hammer is going to drop free fall. You cannot friction around. So therefore, this blue frame must be perfectly vertical. So this I should commend Peter and his team, Marcel. They designed this equipment such that it can be, you have to level, if the thing tilted, it cannot run. You have to position it perfectly straight. There's a lot of sensor here to be checked, to make sure this whole frame is straight. You press the button, boom, run, finish. Okay, that's beautiful. Okay, there are many projects we've done again. If not many hundred, even close to 1,000. Okay, I think video work, so I don't need. Now this picture is showing you one of the many projects done in Singapore. Right, and then I like this picture to show you what is the size of the rapid load test. You see, only this small. Compare with this one, this is still in the making, will come up here. But even this size is much bigger than this. So of course, if your space is big, you have no problem. But sometimes in some project, the parts are very close by. So it's easier to mobilize this. By the way, this comes from 2 containers. These 2 fit inside here. This is a 20-foot container, 2 of them. All these things fit inside here and take out and assemble it up on the side. That's it. So you only have to transport these 2 containers. That's all. Okay. So in comparison with this amount of block, you can see so many block and so many steel plate. All this, all that. All right. So that's a long time. Again, it's the same. The other project again the same. Can you see that? Will support all these come from inside. This is empty now. All these fit. They pack it very nicely, just nice, packed inside. But you look at this, oh, still have a lot to do. And also you can see in the ground is very difficult ground. And even to do the static last year, oh, you have to level the whole place. I mean, there's a lot of things you have to prepare. Whereas for this case, no, you just to make sure that this thing can stand flat. So you prepare the ground a little bit, can stand flat. And the dimension of this, I'll show you later on. It can be as small as 3 meter by 3 meter to at the most 6 meter by 6 meter. Very small. And whether this one, remember we said just now, this can be 10 to 18 to 20 meter by 20 meters. So all this can be very wide spacing. So you see the difference between the two. In city area, but Malaysia, this make a lot of difference. All right, because a lot of sites are very congested. You really need to have this kind of thing. This is just a picture showing very small Singapore. This airport, everybody know this small Singapore red dot, and yet we have done so many. And this is only partial. In fact, we have more. Okay, so now let me come to a very important expectation. When you get a test result, remember just now we say you get a test result like this. This is a load. This is a time, and then you also have the result of settlement, do like this, and bounce back. So this is time. All right, this settlement is low. The power. Remember what is a static capacity? What is rapid make, but a little bit of dynamic. All right, equivalent. That's what we want. Okay, I mean, rapid load test has a little bit of dynamic component. How do I interpret such that I get a static equivalent? Sometimes I lecture, I forget how to spell simple. Equivalent. Okay, static equivalent. How do I get my static equivalent? Okay, so we can skip all this. Okay, come to equation. So this is equation of motion. Simple equation of motion. This is a mass of power now. We're talking about power now. A power like this, I have a mass, drop my heat onto it, okay, and produce that deceleration. Anyway, there's a force here applied. So therefore, this power will move. So when you move, there's an acceleration, there's a velocity, there's the displacement. U is the displacement, which is settlement. Okay, K times U is the static force that we want, static capacity we want. But now we have these two additional components, and the left-hand side is the rapid load that you measure. You measure exactly by the loads. So therefore, what you have to do is very simple. I want the static force. I just have to equal to rapid load test minus the MA minus the CV. That's it. Minus away these two. That's all. Okay. So this is just explaining, but end up with the same answer. Never mind this. At the end, this is okay. This just explain using soil parameter. But never mind that. Eventually end of this simple equation. Just on the 2-3 slide explain in terms of soil parameter, but doesn't matter. At the end is rapid load test minus MA minus CV. Okay, V is the velocity of the power, A is average acceleration of the power, right? And then this is the mass of power. All these are measured because I'll show the instrument later on. You put an accelerometer on top. From there, integrate, can get a velocity, and you know the mass of power, and you measure this by load cell, by load cell. Right? So the only thing you do not know is C. Okay, the only thing we know is a damping coefficient. Damping, that is something we do. Then whole thing can be solved. Okay, so let me show you. So that's exactly what I mean. Okay, I think Prof. Wayan also borrowed this picture and show you. All right, let me summarize this again before I go. So the static test, you need 100% dead weight. If you want to test 1,000 tons, now the mass here has to be equal to 1,000 tons. Of course, I'm mixing the unit now, but you know what I mean, equivalent, okay, to test it. PDA, you are very small. Drop mass is 1 to 2% of test load, of load. Small hammer, brick. You measure the signal and do signal matching. Actually, you do not, I mean, your acceleration, but you do not measure load. You do not measure load. Whether static, you measure load cell here, and also rapid load. Rapid load have two types, Statnamic and Statrapid. Okay. Hyperdynamic, Japan name, never mind this. So the same, you measure load cell blue color. You also measure settlement. You also measure settlement by laser beam, So therefore, you direct measure power load and power settlement, same as static. Different from PDA. That's a major difference. So there's no curve fitting needed. There's no 16 parameter, no need. There's only one parameter, which I'm going to show you how to fit. Okay, so this is what you get. Remember, just I said that when you run the test, you basically measure. Okay, why should I do this? I don't need to do this. You measure the load, measure the settlement, right? Which is what you have here. I don't know why I do this. Never mind. Yeah, you measure the load with time, you measure the settlement with time, the red and the blue line. And then for this point, I have the load Q1 and settlement 1. So I can Q1 and this is delta 1. So I can plot this value. So actually from these two data, I can get this curve. So this is the load settlement curve, except this is under rapid load test. Okay. Now, of course, you can see this curve when the load increase, the settlement increase. But then you will come to a point that settlement is the maximum, which is here. This is maximum settlement point. After maximum settlement point, the power actually bounce upward, right? If you look at my illustration, the power will go down when you load and bounce back. Go down and bounce back. At the bottom, before the power come back, the velocity here equal to 0 because velocity downward is positive, upward is negative. From positive to negative, there's a 0 in between. So velocity equal to 0. Remember the formula just now? Static equal to force rapid load test minus MA minus CV. If this velocity equal to 0, CV equal to 0. So I don't need to know C. I only need to measure rapid load test and measure M and A. I get a result. So therefore, I do that. See, this value is MA. I subtract or plus, depending on acceleration. Acceleration can be negative. So minus MA become plus the value of MA. Minus or plus, doesn't matter, okay? So it become here. So therefore, this is the accurate static force. And let me say this. When you come to this state, there's no assumption made. I mean, the only assumption made is, okay, rapid load test valid for this part. Okay, which we'll talk about later on, related to the duration of load. We'll talk about later on. But basically, there's no complicated curve fitting equation. No, straight away, this is an accurate point. Okay, that's it. But unfortunately, one cycle, only one accurate point. If I don't know the others, all right, which is this equivalent static curve, the other, I need to assume C value. Assume C value from this point and this point, I can calculate C value, which is not too bad. After get a C value, I get this whole blue curve. Okay, so let me summarize. For one cycle, you can have one point is very accurate, no assumption needed. But if you want the whole curve, the blue curve, you need the assumption of C, okay? Which is what we call equivalent static curve. Equivalent static means you treat this blue line as a static curve. You take this blue line, compare with your Thalib test, compare with the reaction power test to stop. That is interpretation. Okay? All right, then to summarize, okay, how come? Okay, let me do the clean. Okay, next screen. Okay, so to summarize, all right, to summarize, we can measure very accurately the load cell. A is a load cell. We can measure very accurately the displacement reflection plate. We measure, we get, of course, the mass, you calculate A. From A, you get velocity. That's all. All right, and then you have the settlement. So from there, you can plot that graph. You can get one static curve very accurately. With the assumption of C, you can whole curve. So therefore, in short, there are two methods. One is called single cycle. I get this point accurately, and then I assume C, I get this curve. But there's another way to do it. If you do multiple cycle, you drop the small mass, this one accurate. This first cycle with the rapid load test. This is second cycle with the rapid load test. This is third cycle with the rapid load test. And every cycle, 1 point accurate. This blue one is accurate. Accurate static value. I don't need the assumption C. I just joined this. Engineer were very smart. 3 point, we just joined it up. That's it. So this will give us what we call static equivalent load settlement curve. That's it. And this one replace static test. That's it. So I compare this red line from rapid load test. I get this static equivalent curve and I compare with static. That's it. And in fact, this is equal to static equivalent most of the case. Okay. Now this line represents the static equivalent very well. All right. And by the way, this method is called, this point is called unloading point. And it's not developed by me, it's actually developed by Peter and the Japanese professor Matsumoto many years ago, 89, 86, 87, 89. Okay, so Peter, yes, he's one to come up with this together with Professor Matsumoto and plus a few people. So they come up with this unloading point and it's still used today and it's still well accepted. Okay, now, and it worked very well for sandy soil, okay? But okay, if you're a little bit more clayey, that's what we call the loading rate effect, because you know for sand, there's no loading rate because we are aware that now the test very fast. Compared with static, where you maintain for a long time, that's what we call loading rate effect. But actually this loading rate is only significant in clayey soil, all right? Not in sandy, sand, no problem. So this one for sand and silt, no problem, or rock. That's what we do a lot in Singapore, okay? But if you're clay, no problem. You modify this to call Sheffield method. And look, actually it's like this. This F rapid load test minus MA, except at the bottom you correct with the loading rate parameters. Can be done, okay? And I will advise you on what's the beta value, what's the alpha value, and then you can calculate. Just a bit more complicated. But that's provided you are in stiff clay, okay? So fortunately in Malaysia and Singapore, most of our pound actually is on good sandy ground. I don't need to do this. I'm happy to do this one most of the time. All right, so far I think we are doing this 99%, doing this 1%. Well, actually we do have 1 or 2 cases that I need to do this, okay? I think that's it. Right, just a quick summary. The rapid load test analysis results are unique and person independent. You see, there's no 16 parameters, and you can give an equivalent static curve. This equivalent static curve is simple and straightforward. There's no signal matching required. And based on this, we can get a very good result compared with the real Cambridge static test, which I will show you in a short while. Okay? Okay, the same picture. I want to remind you on this, and I'll break here. Okay? Okay, let's break for 30 seconds again. Can any comment, any particular question on this interpretation related? Is everybody still there? Hello? Everybody still there?
Here.
Still here, clear? Still clear? Henry, still there, clear?
Maybe it's too heavy for us, Professor Chew.
Yes. Okay,
Maybe Professor Chew, you could explain in again. The concept is, I think, is not difficult for everybody to understand.
Precisely.
The force, mass times the acceleration.
Yeah.
But the interesting thing is for the Statrapid. For Statrapid, you mentioned that there is minus 20 G with that cushion. Yeah. So if you can explain that one more time.
Okay, you see, I have a cushion. This is a palm. This is on the ground. I put a special cushion here. Okay, I have a drop mass. This thing will drop onto it. So this cushion will basically have to compress like this, isn't it? will come to a stop mass. Okay, I change the color. This drop mass here have to come here and press on that. So you compress. And this from here to here, you're subject to deceleration. You're subject to deceleration. For example, you have a spring. You put a spring there, you put a load inside, the spring will compress and then stop. And then bounce, isn't it? So that spring, when you compress, the mass will start from big velocity, go to stop there, and then bounce back. Also, obviously, there's a deceleration because velocity come from big velocity when hit and then come to stop and then bounce back. So therefore, there's a deceleration. Now, if you ask me, Dr. Chew, can you measure this? Yes. The answer is yes, but don't need. Why? Hey, frankly speaking, I don't care. Why? I put the load cell here.
Load cell.
Put a load cell here. I put a load cell here. This is a load cell. Then I measure. I put a 1,000 ton here. To be honest, I put a 50 tons here. I put a 50 ton mass here. If I put a timber cushion, let's say, I put a load cell there, I measure 50 ton force only, roughly. But I put this special cushion, if it work, it measure 1,000 ton. Right, so that is a magic. That is a magic. But of course, you ask me, hey, can you give it a formula for this cushion? Well, too bad. You had to ask Peter. That's his company secret.
Well, basically the drop is gravity, just the same as PTA, right?
Yes.
Say 5% to 10% of the load, and you just drop it by gravity, and then the cushion make the
correct. Yeah, to be accurate, the velocity here is 2g square root. Right? That's what m cancel of 2. That's the velocity at this moment. But you come to here, you got the velocity 0. So how to reduce from here to here? How to design that cushion? That is tricky. That's tricky. But let me, to be honest, I work with Peter and myself for 20 years. Concept is what? But how to make the machine so neat and so nice, honestly, not easy, to be honest. And then you should salute the ornament people. They really make that nice machine, to be honest with you. Yeah, I mean, for whoever want to think that, hey, I can make myself, go ahead. But I tell you, to make the machine really fit well, actually not as easy as you think. But anyway, that's a concept. Good, you asked a sharp question, Ryan. Okay. All right, so let me continue by another. Yes.
I have some question. The cushion used the principle of a spring, right?
Repeat, principle of?
The cushion used the principle of a spring.
A spring, yes.
Yes, spring. Yeah. As we know that the spring will relax of time.
Yes.
Is there some kind of calibration that needs to be done?
Yes. Very good question. That question, I'm not going to answer here. That question tell you need good company, constantly calibrate the spring to produce good result for you. Full stop. But you're right. You are right. The spring, if you load it many times, the constant will change. Then the result will be different. So that's what I'm trying to say. Concept is there, but anybody think that I can make you can do well, go ahead. It's not as easy. And do this. Spring need to be, the property need to be constant, properly calibrated. That will give you the one. But as engineers, this limit to, I'm concerned, I only look at the force and measure. I look at the force and measure. I want the force to be this number. You must produce this force for me. That's it. Okay?
Okay.
Can I answer
we have
you this way?
Question from Pak Amin Sundoro. You raise hand.
Yep.
Silakan, Pak.
Yeah. Mr. Chew, can I ask something?
Yep.
By the way, how much does it cost? Is it cheaper than Cambridge or more expensive than PTA?
Okay. Good question. Anything related to money? I am a technical advisor to Dynamic. I do not know anything about the money, okay? But to be honest with you, in Singapore, the price is very competitive with static load test, okay? But of course, I know the different country, the static load test price can be very different, okay? But definitely it's more expensive than PDA because PDA is too simple and PDA, but you don't forget the objective. This test is to replace static, it's not to replace PDA. I don't care about PDA. In fact, in Singapore, maybe I should expand this a little bit. In Singapore, we do not accept PDA to give us the static load settlement curve. No, although PDA can give this curve, but it's not valid. We only use PDA and QC for power quality, like PIT, but more advanced PIT. You know my point? So we don't, unless you are steel pipe power, so sometimes we do. But in general, for ball power, we are not accepting PDA. So okay, anyway, as far as money is concerned, yes, that's out of my jurisdiction. I don't care. But I will say that, yes, if you have a lot of tests, let me to be fair to the company, if you have a lot of tests in Indonesia, like what we have in Singapore, put a machine there, actually the price of that is not high. But at the same time, to be honest, you have to think that the value you get is actually, to me, it's just that you buy a better machine, better equipment that tests better than static tests, faster than static tests. You should charge higher. Why are you charging lower? Okay, anyway, this one we leave the discussion to the other meeting, okay? To privately meeting, okay? Yeah. But I can assure you it can be competitive. Not compared with PDA, but compared with static. But of course, I have to say that the static sometimes in different country will have a different, totally different scale. You have to think about the value of this test. Much faster, very accurate, you get a result on the spot. Think of this, you don't mind paying money. Just that you pay good money for good transport system, high-speed rail rather than normal old train, right? You cannot compare the good train versus a slow train. So it's different comparison. Okay, I tell you what, give me another 10 minutes to 15 minutes. I share with something else on the code and correlation quickly, and I'll open the floor for all questions. Okay, code just yes in Japan, people do even earlier. Code 2016 or approved. In fact, more. And Singapore, of course, make use of it. Malaysia, we expect. Okay. Now, so this is what we call. I think Wayan will show you like that. ASTM 7388208. Of course, there's a subsequent yearly approval.
Recording in progress.
Now, into has the state to tell you that whatever test here come from. Okay, this one. Correctly, so that at the important. So drop, you think that's a test, I'll tell you not satisfied. Yes, so therefore, concept looks simple. You want to make satisfied as you think. Okay. There's a requirement there, but I'm displacement, my message, but high speed dynamic PDA does not satisfy this. I just want to say that. And this duration is 12 L over C for the bottom for the zero load or 4 L over C. Meaning this time, this duration here, the duration must be this time more than 4 L over C. L is a power, C is a compression wave velocity. Okay, so So the longer part, you need longer this duration. Now, PDA is like this only. Okay, PDA, the duration or time is too short. That not satisfy this. Or it's not only short, it's short a lot by 10 times, that kind of thing. Okay, so therefore, you have to understand that. Huh? Now, again, as I say, so this time has to be 10 times LVC. Of course, the longer it is, the better it is. Huh? So that's the reason is that is so that the wave will travel up and down many times. So therefore, this rapid load test, the wave compression is not important. PDA is here. Can you see only one time or less than one time? So therefore, the wave propagation effect is important. So therefore, you need to do signal matching. But whether rapid load test, I don't need. Right? It becomes a rigid body movement, things like that. Oh. Okay, so I think that's about all that I want to cover for this due to time constraint. I just want to have one word to say that if you want to do instrumental power, meaning you measure the power shaft resistance, so you put strain gauges along the power shaft, along you do the same thing. The only thing in the type of strain gauges, you have to use what we call, we cannot use vibrating wire, but you must use the resistant type strain gauges, which is the old method and established. To be honest, I'm sure today all the old professor on piling your research is done on this. Vibrating wire is a new one, which is good, except the vibrating wire, you take the reading at 1 hertz. 1 hertz means 1 data per second. Now you remember, my whole cycle test typically from here to here is 200 millisecond, 0.2 second. You understand my point? So in 0.2 second, the test over. So I need a lot of data. I need a lot of data point. But if you do straight what is that? The vibrating wire, you have 1 point, you have 1 data here. Next data is here. I mean, it's over. You know my point? You cannot capture this curve. But don't worry, you just use the old traditional resistance type strain gauges, which is in the market for 70 years. All right, it's perfect. Okay, so I just want to remind you on that. Okay, now last but not least, what I want to share is to prove to you that this is compared very well with static. Okay, so I'm going to show you a few slides. This is very important so that you're confident. Okay, so I'm going to show you a few jobs that I can skip this introduction. Okay, I skip this introduction. I skip all this. I skip this one. I just want to show you correlation of dynamic versus static test in Malaysia with different power, even different power diameter. But for different power diameter, you must normalize it with the diameter. So you can see that we have done 2 tests, or many. I just show you one. One case that the power length and then load is different, and then settlement, we conduct that, and then we get the test. This is a dynamic test. And then this is a soil data. We can skip. This is a test result. This is static test. This is dynamic. And again, it's 1 point accurate. This one with the C assumption of C. But still not too bad. So now you put the static, right? And then you put the 2 together. Unfortunately, they are different diameter, but you correlated it. That's what you get. One is static. One is dynamic. But of course, dynamic have to go to unloading point method, go to static equivalent. When I tell you rapid load test means rapid load test go through the unloading point method, then get the static equivalent, which is this red curve. You see, the comparison is very good. For engineering, this is like few mm in Malaysia. Now, in Singapore, we do a lot more powers in just now was dynamic. Now we do a lot in rapid in Singapore. You can see this one. We have again many hundred. But let me just highlight the number to you here. Okay, sorry, I want to highlight 2 number. So this one, you can see this is the rapid method. We just look at the last one. 3 times working load, 21 mm, and you look at the other one. You look at, I'm moving away this, 19 mm. Static. Sorry. So this one you convert, you get static equal to 19. So I should ignore this one. So this is rapid load test, rapid test. But after getting static equal to 19.63, and this is static load test by Kenlich method, 19.63. But this is this is coincidentally exactly equal. Okay, but I can see how good is a match. And look at this. This one is an instrumental. So we load the load transfer, we can measure load transfer curve. At one particular load, this is red is static, one is dynamic. See, perfect match. See, one is static, this is static. Static means the cartilage, huh? This is cartilage. And this is a rapid load test. Again, let me repeat. Rapid load test, then do unloading point method, and then get this so-called equivalent. Okay? You compare, you see? Hey, you may say, hey, not exactly, but look, this is only few mm, this is only 2-3 mm things. You see? So it's very close. And then you look at the exact number, actually it's almost matching. There's one. Second one, can you see the two curve? Right, and this is 5 mm. From here to here is 5 mm. So you can see this is static and rapid load test, very close. And look at the number again. This is, which one is static? This is sediment was static. Cartilage. Cartilage average is 19.96. And rapid load test is 18. This is more, I like this one. Different by 1 to 2 mm. That is more correct. I like this one. Just on the one is exceptionally accurate. But a lot of time we get 1-2 mm different, which geotechnically is perfect. Okay. Now let me show you, right, more result by Ricky Nagati. I show him because he's a director HDB, and more important, he is Indonesian. Hey, he's my good student. He's my student NUS, and he works for government HDB now. And he wrote the paper with me, right? And we just presented in a conference last year in Rotterdam, correlating rapid and static load test result in Singapore. And look at the result. We have done many tests, compare cartilage, and we do the cartilage first, then do stack rapid. We also do stack rapid first, do cartilage on the same pile of different type of soil. The detail I'll show you next time if you want, but this is the result. This is settlement for rapid load test. This is a settlement for static load test. And this is 1-to-1. You can see, Dr. Chew, it's not on there, it's different. Hey, but look, this is 1 mm. So at the most, this is what? Less than 2 mm different. Let me repeat. This is 1-to-1, perfect match. If all the result on perfect match, I tell you, that's cheating. In geotechnical engineering, if you match 1-to-1, it's cheating. But you see, all my data is different by not more than 2 mm between the two tests at one particular load. In this case, it's 1-time working load. If you get 2-time working load, can you see? All these are good except this point. This again 5 mm. So this about again 2 mm. This one a bit big. That is because I did not take into account the so-called second cycle effect, which is what I call virgin over residual, so which I explain next time. But if you take that into account, see, same data. These two are the same data. 2-time working load. I put it to 3 times. You can see the biggest difference here is this is 5 mm. So this one is obviously 2 to 3 mm. In fact, less than 3 mm different. You see the point? So let me repeat. So in Singapore, Malaysia, most of the tests that we get, correlation can be as good as settlement within 2-3 mm when you test up to 2-3 times of working load. And that is what we're interested in. That's what your high-rise building are interested. Okay, of course you can compare the ultimate load, but in Singapore, Malaysia, we like to compare the settlement at 2-time working load because that is important for your proof load test rather than ultimate load test. Finally, on productivity, I can skip all this. I just want to show you this is a big project in Singapore. Skip, just see the last number. Okay, wait, where's my, I want to move this board away. Hey. Okay, this, okay. Important one is normal cartilage test takes 16 days because in Singapore, because you got to transport all the block, 16 days, and this one 3.5 days. Like rapid. Next project is a big power. Can you see? I test 4,000 ton. It's a big barrett power, which is for the MRT. MRT is our mass rapid transit, like your subway, light rail piers. It's similar to your power bridge pier, that kind of thing. Big power, big diameter, big power, big load, and we test and location. You see, cartilage you need this high, but Statnamic only this high, this much. Okay, and then the footprint number can skip this one. Hey, because that's a super big. So therefore, the conveyor cartilage need 2 months. And I need 4 days, 3.5 to 4. No matter how big, how small, 3.4, 4 days. Okay, that's the beauty. Of course, to be fair, transporting from Singapore equipment or Malaysia to Indonesia, separate day. Professor Wayan, you cannot say, hey, Dr. Chew, you said 3 days. You ship the thing in 3 days. No. Shipping excluded. When you're in the port, you go there 3 days. Okay, perfect. And in fact, HDB has analyzed this number. Of course, this is in Singapore. Typically, static handlage test take 80% reduction in productivity, reduction in manpower and time in manpower, and overall land is 85%. So overall productivity is very good. That's all. Okay. Yeah. And wow, we love to look at all these things. Manpower, man hour need, things like that. So we save a lot. Okay, I think that's it. I just want to end with a summary, conclusion, 3 sentences. Okay, let me read it. All right, number 1, the load settlement behavior of the test pass subject to static load and rapid load are very similar, so therefore correlate very well. Correlation between 2 tests, rapid load test and Statnamic and static load test, are found to be excellent in terms of specific settlement value and specific load settlement response, which are most of the time we want, load transfer curve, mobilized skin friction, mobilized end bearing, compared with static. They're very equal. They're almost identical most of the time, provided you do it properly. Provided your spring, I think, who was there to ask? Adib, right? You asked a question. The spring must be properly calibrated, conducted properly, proper equipment. You get very good result. So finally, a safe, productive, and easy to use device become available, which allow power tests to be performed economically and reliably, and what's the last word? Beautifully. Maybe that beautiful word should end my lecture today. Okay? Now it's 5:50, sharp, 6:50, perfect, 4:50. Okay, thank you. That's all my lectures. Yeah.
Okay, thank you, now, Professor Chew, for your explanation, presentation.
Yeah.
And we still have time, maybe not much. Yeah. If you have some question, Bapak Ibu, kalau ada pertanyaan silahkan ditanyakan Bapak Ibu. Profesor Chew ini lebih ke sisi teknisnya, untuk sisi bisnis perusahaan, vendor dan semacamnya mungkin bukan ke Profesor Chew, tapi mungkin nanti ada perusahaan yang akan memperkenalkan juga nih Pak. Saya belum tahu juga Pak Heri, mungkin nanti kita ada informasi Bapak. Silakan Bapak Ibu kalau ada pertanyaan.
1 Pak Adib, kalau bisa Pak Adib. Pak Tianto.
Pak Tianto.
Thank you, Prof. Chew. I'm sorry, I'm in Indonesia because my English is not too fluently, bad in English. Yeah.
No, I hear you clear, sharp.
Oh no. Please Pak Adib, tolong sampaikan Pak Adib. Kita masih agak mungkin harus memang ke sana ya arahnya ya, tapi kan perlu waktu. Ingin menanyakan ke Profesor Chew, Pak Adib nanti, punya nggak experiences dari Pak Chew itu tentang bagaimana kita menggaransi bahwa keakuratan dari alat ini ya, kegagalan atau value dari suatu hasil gitu ya, itu apakah kegagalan itu memang kegagalan di pondasi atau kegagalan dari alat itu siapa yang mohon supervisi ya. Kita butuh ini sih garansi benar dari perusahaan bahwa sistemnya benar-benar akurat gitu ya, sehingga kalau ada suatu kelemahan itu memang itu benar-benar filenya yang lemah di dalam kapasitasnya. Itu mungkin ada pengalaman kegagalan itu pada Pak Chew, bisa ditanyakan Pak Adib. Terima kasih Pak Adib.
Baik, terima kasih Professor Chew. The question from Pak Tianto is, how do we guarantee the accuracy of this tool? If the result is failed, is it the file that failed or the tool that failed? How to guarantee if the result is failed?
That's a very good question. In fact, your question itself answer for it. Meaning that if the result is no good, there are 2 possibilities. One is the test is lousy.
Yeah, not fail but not good.
Yeah. But the second one is the part itself is no good. Yeah. In fact, I was telling you a joke. in Singapore, I don't quote the man, one very high official in government authority. He told me one sentence. He said he's a government authority who control, I mean, he have all this power result. He said that for the last 20 years, he never see a single PDA result that show the power fail.
Oh.
Contractor always submit the PDA result that pass. But I will tell you that for Statrapid test, actually we do have a few cases, the result no good. No good means a power plunge. And later we do a check. Is a power structural failure or geotechnical failure? Yes, we do have that. So in fact, good point that you mentioned that. I remember just I mentioned about the paper we present in Rotterdam last September conference. I wrote another paper on the shape of the rapid load test curve. From the shape, I can tell you a power fail or not. And then with that, we check. So in that paper, I highlighted a few real case study where people run PDA test, cannot detect, but run the rapid load test. We tell them, look, the power problem, right? You have soft toe problem or your structural a gap, the power can crack in between. The rapid load test will pick up. And in fact, for a few jobs, we do the calling to prove what we say is correct. Now, so in short, yes, I will answer you that rapid load test will be able to detect if the power fail, really behave fail. Because, let me have one more sentence. Because you put the real load on it, 1,000 tons. The PDA only put a few tons only.
Yeah.
That's the main difference.
Yeah, great.
Yeah. I hope next time I'll show you the real data, but take my word, we can show.
Hey, thank you, Mr. Chew. Yeah.
Welcome. Good.
Yeah.
Bapak Ibu, yang lain silakan.
Yeah.
Excuse me.
Silakan Pak.
Mungkin saya Putra dari Kementerian PUPR, Direktur Jenderal Perumahan. I'm Putra from Minister of Public of Work. Maybe I want to know about what kind of type foundation can be test by the rapid load test method. This one, and how many times I need to test for the get good result to the test. Okay, thank you, Mr. Chew.
Good answer. Good question. What type of foundation you can do? Power foundation for building. Power foundation for bridges. Even a power if it's in the water. Remember, you build a bridge, some of the power will be in the water. Even that is very good to use Statrapid or Statnamic to do the test. Okay? And you can do that. So any power foundation, you can do it. Okay, now the second question is, how many times you have to do the load? Now, Statnamic, because Statnamic has this fuel, you blow it one time, it's a bit difficult to take down and put it again. So normally we do one time, boom, test. You get 1 point accurate. The rest of point, you assume some C, get to be not too bad. I will say this honestly, okay? So that's one time. But the Statrapid, the cushion one, for the same power, you set up, see my hand, like this, boom, one time. 10 minutes later, boom, second time. Then 10 minutes later, go up, boom, third time. Go up, boom, fourth time. I can do 4 times. 3 times to 4 times. Good enough. But must be some small to big, But I say, hey, what if I test 10 times? You can go ahead, but don't need. So you need only 3-4 times to get a good result. Good or not good result, let me stress one more time, like what Adib have said, Putra. Good equipment, good spring, proper conduct is very important. If you have all these 3, you don't need to repeat the test. So far in Singapore, I don't think we never have to repeat the test. Every test result come up, very good, consistent. Yeah. I hope that answer.
Thank you, Prof.
Professor Chew.
Yes,
silakan Bapak Ibu lain.
I want to ask you about would we use the best operator, skill operator or not?
Operator, is it important? Yeah. Setting up is important. the operator, the dynamic machine, everything automated. If you set up properly, the engineers is going to look at the screen. Okay, I didn't show you because this one, it could be the real project. I'm sure the dynamic will bring the equipment and show it to you. Everything connect to a PC computer. You see every data on computer. Remember, just I tell you, the thing must be balanced, must be set perfectly. So all the tilting number on the computer, every night, just press the button, start, boom, turn the test. So operator, I would say, is a setting up that's very important. You need the right company, the right equipment to set up properly. To run the test, it's different from PDA. You need the people live up or whatever. No, this one is everything connected up. Press a button. Everything. Marcel, you want to add on that? Everything automated. Yeah.
Yeah. How many samples we need for
how
testing?
many?
How many person? How many percent?
How many person you need?
The pile. How many percent of the pile?
Must you test? Oh,
yes.
That's not for me to answer. That's for Professor Wayan and for Harry in your committee. In Singapore, we test 1% of the pile as a working load test. Meaning that if you have 100 piles or if you have 300 piles, I must test 3 piles as a working load. Means test up to 1.5 or 2 times working load. So now in Singapore, all these 3 piles, I don't have to do cannage. All the working load, I can use rapid load test. After you calibrate, you can do rapid load test in Singapore. Now, if you do ultimate normally is 1 per block. Singapore, we do 1% of the pile. Yeah.
I mean,
I should say, wait.
In Indonesia.
I should say this, wait. Professor Wayan, just one more. But for bridge piers, for LRT, all this, every pier we test 1. Imagine you have the bridge. The bridge has 2 piers. This pier have only 3 piles. These 3 piles, at least 1 must test. This side 3 piles, at least 1 must test. Because the bridge is so important. so that one cannot go with the percentage. Go with every piers you will test. Yeah,
for Indonesia, Pak Peter, as I mentioned, yang seperti yang saya bilang di awal itu kalau kita secara umum di SNI Geoteknik kita mensyaratkan itu 1%, 1,3% untuk bore pile, kemudian 1%, 1% for the driven pile. So that is general requirement. But for bridge, there is no exact, no clear, requirement. But that general requirement is maintained for, various for building, for bridges, and others. No.
For bridges, the number of power definitely less. So, but the percentage will be very. I mean, like I say, you definitely have to test 1 per pier.
Per pier. Yes, that sound reasonable, because like building in one area we have 1% or 1.3%, but for bridge you have a lot of pier that spread, so the uncertainty there is higher compared to the footprint of the building, right?
Yes, definitely.
Excuse me.
Ali?
Yeah, my name is Ali. From Directorate of Bridge Construction. Thank you, Prof. Chew, for the lecture. I have a question for you. How about the huge force that distract the top of pile? Temple made from concrete. Yeah. Is this method more damaging to the top of pile rather than a static pile, which is using gradually load?
Good question. Ali, you must be a very few people. Good question. The straight answer is, therefore, proper design, proper company is important. You know why we do 20 times, don't do 40 times? Because F equal to MA, I can make the A equal to 40 times G. No, you see, so therefore, the reason we do that 20 or sometimes 22, 25 or 15 times, so that we have to check the maximum load applied on the pile cannot be more than the structural capacity of the pile. So you're right. So if your pile is concrete of grade 35, meaning the compressive strength is 35 MPa, the load that we apply cannot be more than 35 MPa. But it's safe. You know why not? Because remember your design is the ultimate load divided by cross-sectional area that has to be less than your concrete compressive strength. So if I test working load, 2 times working load, it's definitely less than ultimate. I divide by the cross-section will be less than your compressive strength. Will be less. Okay, but you asked a very good question. To be honest with you, this is a secret. This is a secret. Actually, we can measure based on the signal we receive, based on the acceleration. Actually, we can calculate what is the maximum load that experienced in a power. If that exceeded your compressive strength, the power will fail. In fact, that was one of the failure I can predict. So my answer to short, if proper design, 2 times working load, full load acting on a power cross-section should be less than your compressive strength. To stop. So 99.9% time, no problem. If we measure the force is bigger, that means your concrete got problem. Concrete got problem. So it exceeded, it failed. Indeed, I told you, right? PDA will not be able to pick up this, and we can pick up it. In fact, in Singapore, we pick up 2 times exactly like this. Out of a few hundred. Yes. So don't worry. Yeah. It's the contractor to worry. If the contractor use lousy concrete, you're worried.
I get the point. Thank you, Prof. Chew.
Good.
Sudah jelas. Baik, pertanyaan berikutnya kita mungkin sampai 5:10 ya, Bapak Ibu, kalau ada pertanyaan atau diskusi. Maybe we have discussion until 5 to 10, Prof. Chew.
Until 10 midnight, yeah, correct. I'm happy. I love that lecture. People stay back, but of course, cannot go too long. Okay, now you control. Yeah, Chairman, you control.
10 minutes after 5 minutes.
Yeah. Yeah. Maybe we can take the last questions. Yeah.
Yes, last question maybe.
Yeah. Don't worry, if you guys have a lot of questions, you just tell Henry and tell Professor Wayan that you love to see me. I love to come to Jakarta and face to face, and we work on the project. I mean, if you do project, I'll come, and then we discuss.
Pak Sartowi, ada pertanyaan, Bapak?
Nah, saya yang tanya tuh.
Oh, Pak, silakan, Pak.
Yeah, because my device no unmute button, yeah. So I would like to ask you about the deviation of the diameter pile, bore pile. In case of the NKN, yes, it's only one single diameter. If we have many, then this device can be applied simple or many kinds.